In this video, we consider the problem of a box placed on an inclined plane. The box is experiencing the force of gravity, which wants to pull straight down, but the inclined plane forces it to go along a 30-degree angle. We'll consider the problem first with the frictionless ramp, and then considering the ramp to be made of different materials, which will change the amount of friction that is placed on the box. So let's see how this all plays out. So the problem we're given, we have a 1 kilogram box and it's sitting on a 30-degree incline. It's always useful to draw a sketch when you're solving problems. Just draw a little sketch of this. So here we have a 30-degree incline and we have a box sitting on this ramp, and that box has a 1 kilogram mass. The box is made of copper. That will play a role later when we consider the ramp to be made of different materials. The amount of friction that is experienced between one material and another depends on what both are made of, and you can look up tables of these numbers. But for today, I'll just provide the numbers that describe the amount of friction between copper and glass and between copper and steel. But first, let's consider the ramp to be frictionless. Okay, so another thing besides the sketch that is useful in a problem like this is to draw a free body diagram. So in this first case, our free body diagram, I'll draw the box on this slight angle again. It's going to experience the force of gravity that wants to pull it straight down, but it can't go straight down because it's sitting on a ramp that's on a 30-degree angle. So we can break that force of gravity up into two parts, one that goes straight into the ramp and one that goes along the direction of the ramp. And let's call this the perpendicular part of the force and the parallel part of the force. And that's the gravitational force acting on this block. Now, the ramp also pushes back, so the box isn't going to be going into the ramp or floating up off of the ramp. It's going to sit right on that ramp. And that implies there is a sum of zero of the forces that are perpendicular to the ramp. So it must be completely balanced out by that ramp pushing back out against the gravity. So this perpendicular force is completely canceled out by this normal force from the ramp. However, there's nothing stopping this force. It will cause the box to accelerate down the ramp. So let's find what all of these forces are. Our full force of gravity goes straight down. Try to draw that a little more vertically. There we go. There's our force of gravity. And we will break this up into two components. One that goes along the ramp and one that goes into the ramp. I'll try to draw that one again too. Oh, there we go. That's a little better. So notice from the geometry of my triangle here, gravity is going straight down. And here is the 30-degree angle. This angle here, considering that this is 90, we have to have 60 degrees on this one. And this 60-degree angle is the one that matches this corner of my triangle for breaking down the gravity into components, which means that this is the 30-degree angle down here. Now I could work with the 30-degree angle or the 60-degree angle. It doesn't matter in doing my trigonometric functions, but let's leave it this way. And this, of course, is a 90-degree angle there. Okay, so the full force of gravity is going to be the mass of that block times the gravity, right? So we've got 1 kilogram block times the gravitational acceleration, and that will tell us how much downward gravity wants to pull that block. And then the amount of that going along the ramp we'll call F parallel, the amount going into the ramp we will call F perpendicular. That's a sign that's often used for parallel lines, and this is a symbol that's used for perpendicular lines. So, knowing our trigonometric functions on a triangle, this side is opposite of the 30-degree angle. We can find that value by taking the hypotenuse, which is mass times gravity, and then times sine 30 degrees. For the perpendicular component, it will be similar, mass times gravity, but this time that is the adjacent side to the 30-degree angle. So we have cos 30 degrees. And let's just leave these in this algebraic form for now rather than solving them on a calculator. We can do that in the end. Our goal here is to find the acceleration. So once we find this force, we'll be able to find how fast that block will accelerate down the ramp. Okay. So we know that the normal force here, let me just pan back a little bit, get that triangle, or get this free body diagram in view. This normal force exactly equals the perpendicular force, except that it's in the opposite direction. And we don't really need the normal force for this problem. That'll be useful in the second step when we want to calculate friction. For this first problem, we're only interested in how much of the gravitational force points down the ramp. And that's our F parallel, given by this formula here. So let's find that out. F parallel, well, okay, let me back up one step. What we want to say is our sum of forces in the parallel direction is going to equal mass times acceleration. And we only have this one parallel force. This F parallel is mass times gravity times sine 30. And that is going to equal the mass times the acceleration of our block. Notice the masses cancel out on both sides, and we're just left with acceleration equals g times sine 30. This is why it's nice sometimes not to put the numbers in early, because you get these nice cancellations. And then putting in that g is 9.81 meters per second squared, and sine 30, well, let's just leave it as sine 30, but that happens to work out to be 1/2. And we end up with our answer. Just pan up a little. Of 4.905 meters per second squared. Okay, so here's our answer. The box goes down the ramp at 4.905 meters per second squared. Okay, now what happens if we add some friction? So first we will consider that the ramp is made of glass, and I've gone ahead and looked up the coefficient of static friction and the coefficient of kinetic friction for a copper box on glass. And for copper and glass, we find the static friction is 0.68, and the coefficient of kinetic friction is 0.53. Oh, sorry about that. I keep going to pan and I accidentally zoom. Okay. So now let's draw a free body diagram again. It'll be very much the same as before, but we've added a new force. So this time, it's a little steep. Let's make it more like this. There we go. So we still have our F parallel from gravity, and the box is still the same mass, so we're still going to get the same expressions for F parallel and F perpendicular. So that all works out the same as we did in question 1. The normal will be the same, but this time we have this little force of friction. Now, when you have a problem like this and you don't know if the box is moving, so we've got a static coefficient and a kinetic coefficient, you have to first check, is this force pulling the box down the ramp enough to overpower the static friction? If it overpowers the static friction, then it will move. And if the box is moving, you then no longer need the static friction, you only need the kinetic friction. Oh, and I see I forgot a digit there. So the kinetic friction is actually 0.53 for that coefficient. Okay, so we found F parallel above, or at least we have an expression for it. Let's find what our friction force is. So the static friction force is going to be the static coefficient of friction times the normal force. But this normal force is just going to be equal to the part of gravity that's going into the ramp, because it exactly balances it out so that the box, doesn't float up off the ramp and it doesn't go into the ramp. So this Fn, the normal force, is just equal to that perpendicular force. Let's go back up and find what our expression was. So here's that perpendicular force. It was mass times gravity times cos 30. So that's what we want. And we also need to use this coefficient of static friction to see how much, the friction is based on that normal force. So, well, let me finish writing this one out. So this is mu s times mass times gravity times cos 30. So we've got our 0.68, our mass is 1, gravity is 9.81, and cos 30, we'll figure that out as well. Okay. So just pulling up this calculator I downloaded that I can use online here. We've got 0.68 times 1 times 9.81 times cosine 30. And that works out to be 5.777. Now the question is, does this friction force overpower the gravity that's pulling it down the ramp, pulling the box down? So let's find that parallel force of gravity as well. If you remember from above, that's just mass times gravity times sine 30 degrees. And this works out to be 1 kilogram times 9.81 meters per second squared times sine 30. And sine 30 is just a half, so I know this works out to be 4.905 newtons. Now, we can see that 5.777 is bigger than 4.905. So the box won't slide. And we didn't actually ever use this, but you would only need to use the kinetic coefficient of friction if the box does slide. So you first check if the force pulling the box down the ramp is bigger than the friction or not, the static friction. And since it's not, the box doesn't slide. And that question is finished. Just write out our answer. So the box does not slide because F parallel, the amount of gravity pulling the box down the ramp, is less than the static friction. Okay, so third situation, we have a different material. This time, rather than having the box sit on a glass ramp, put it on a steel ramp, and even though the box is still copper, that coefficient changes, or those two coefficients change. So let's see what the situation is this time. Okay, so now we have the copper box sitting on steel. This time our static coefficient is only 0.53, while our kinetic coefficient of friction is less at 0.36. The setup is identical to above, except we've changed the material. Our F parallel will remain the same, but our static friction will be different. We have a different number for this. So let's just put in that formula again. So we find our static coefficient of friction. We have, this time we have a different coefficient. Let's just write it out. Mu s times mass times gravity times cos 30 degrees, which is 0.53 times 1 times 9.81 cos 30. Okay, let's figure out what this is. We have 0.53 times 1, don't have to put that in the calculator, times 9.81 times cosine 30. Okay, so this time our static coefficient, or static friction, is a little less, 4.503. And as I mentioned before, our parallel component of gravity hasn't changed. It's still 4.905 newtons. So I'll just write this down again, but it's the same as we found above, 4.905 newtons. The box is going to move, right? The box moves because F parallel is bigger than that static friction. We're not done though now. We know the box is moving. We can't go and find the acceleration based on the difference between these. When the box is moving, this is not the friction the box experiences. The box will experience friction based on the kinetic coefficient. So kinetic means moving, static means not moving. So you need to check this one to see if the box moves, but if it does move, then that friction force is actually the kinetic friction. And it's a little smaller because you use the kinetic coefficient. And most materials have a kinetic coefficient that's smaller than the static one. Not in all cases. Some materials can be strange, but generally this is true. It takes more force. Oh, I put in sine. I need a cosine here. It takes more force to get something moving than it does to actually keep it moving. So this time we have 0.36 times mass times gravity times cos 30. And what do we get this time? 0.36 times 9.81 times cos 30. And that works out to be 3.058. Okay, so we don't get as much friction this time. It used to be it was 4.503 if the box is at rest. But if it starts moving, there's less friction, and it's 3.058. The gravity pulling the box down the ramp is still what we found before. The acceleration is going to be given up by summing those parallel components of the force and dividing by the mass. And this time we have pulling down, there was 4, well, I'll write them out. So we have that F parallel, subtract off the kinetic friction, and then divide by our mass. Our mass is just 1, so that'll be easy. So we have 4.905 newtons, subtract 3.058 divided by 1, and this works out to be 4.905 subtract 3.058, and that's 1.847. It's in meters per second squared. As long as your mass is in kilograms and your forces are in newtons, the units work out. You have to worry about unit conversions if you're given grams or some other unit for mass. But this works out to meters per second squared, and that's how fast the box goes down the ramp. It's important to give the direction. The box could be going up the ramp. That would be silly because we only have gravity here. But in your final answer, you should always give a direction. So the box accelerates. Down the ramp. At 1.847 meters per second squared. Okay, so that brings us to the end of the video. I hope that helps explain to you how to break gravity down into 2 components, along the ramp and into the ramp, how to find the friction based on the normal force, and what to do with these 2 different types of friction, the static friction and the kinetic friction. Of course, you can have more complicated problems where the box is being pushed as well. Everything we did here still applies, but then you have to add in any other forces on your free body diagram that the question describes. Okay, bye for now.